Alright guys, let's first kind of try to remember what it was we already talked about. It's been a little while. It's pretty much what we're going to do. Alright, so what I won't do is re-explain where these came from. Those really are just the definitions of cosine and sine. But what we're looking at them like now is a conversion between our normal little go 5 blocks over and go 6 blocks north, and then you'll get to where you're going. That kind of thing. This XY plane. Now we're going, if you're in the middle of a field, you can tell somebody will turn by 20 degrees and then walk out 28 feet, and that's where I found the crop circle, right? Or whatever. Alright. So we did this one already, but just remember how this works. What's what in this point? Good. So it's r theta. So how do I get the x piece? If I want to convert this back to rectangular, how do I get the x piece of this?
2 cosine of 4 pi.
Yeah, x will be 2 cosine 4 pi over 3. Y will be 2 sine 4 pi over 3. What is cosine of 4 pi over 3? What quadrant is that in? Third, because it's a little more than pi, right? And pi is the line back here, dividing the second and third quadrant. So it's in the third quadrant. So everything should be negative, right? So what's cosine of 60 basically, and then just put a negative on the bad boy. This would be twice. Good. So it'll be negative 1. And so sine of 60 must be the other one. Must be the other one. Negative root 3 over 2. You're all just like, yeah. And of course, what's the point then?
1.
Yeah, negative 1, negative red 3. Cool. Alright, so part B would work the same way. I'm not going to do part B again. So that's nice. When you're converting from polar to rectangular, it's kick-ass. These are really, really easy to remember because you already know them. Hopefully, you should. The ones that are kind of new but aren't really new, we just are using them in a different way. We know this, that's true. Period. I mean, that's just true. And we know this is the definition of what tangent is. Right? The thing is, you might want to write down next to this, just to make this really clear. When you're using these, you normally go all the way down to theta, right? I've got to figure out what theta is, so I can write that point. So I do the inverse tangent, y over x. And what do you have to be careful about? Any inverse trig. Because our point could be in which quadrant? Any of them. Shit, it's inverse tangent, will it give me answers in every quadrant? No, so it's always going to give me a reference angle. It might actually be the angle I want, or it might truly be a reference angle. You got to figure out what I want. Alright. So just to remind you guys, on part B, for example, what would R be? How do I figure out what R is?
Square root of 3.
Yeah, square root.
Plus 1.
So this is in, what is this currently in? What coordinates?
X1.
Good, xy. So then r squared equals that. So r equals the square root of x squared
2.
plus y squared. Cool. So what do you get for that? You get 2 fourths plus 2 fourths is, that's crazy. And the square root of 1 is, that's awesome. Now this is a good example of one where I don't even need to apply, I shouldn't even need to apply this. I shouldn't have to apply that. What I mean by that is, what angle am I at for that to happen?
45.
And in which quadrant am I in?
2 seconds.
Yeah, this is negative positive, so negative, the second quadrant, right? So what's the angle going to be? It's got to be a 45-degree reference angle in the second quadrant. So what angle is that?
135.
Beautiful. Say it to me in radians.
5.
3 pi over 4, kick ass. So what's the point? 1 comma 3 pi over 4. Bless you. How we got so far? We did okay. All right. Stay with me now. I think we did these. Just remind me. Now we're converting equations. So we're not plugging and chugging. We're replacing whole chunks of expressions with their xy expressions in this case. So of course r squared is what in terms of x and y?
X squared plus y squared.
Yeah, so I replace this with what it is. And what's r sine theta?
5.
Y. And we talked last time about you could subtract the 5y over, you could complete the square. It would be a circle whose center has moved. You guys semi with me on that? Do you guys remember talking about that? It's been a while, I know. And we even did part B. Part B is a little bit freaky, but think about what this thing would look like. Well, this is a little weird. We haven't talked about this yet, so shoot. Let's do this. I'm just dying to freaking get to where we plot points. Somebody out there must feel the same way. Let's do a little bit of point plotting, because then I can talk a little bit more interestingly about this. All right. Very strange sentence. You guys, are you going to be interesting, Jeff? Or are you going to... Alright, look at that bad boy. So I can still see my xy plane on there, right? So what I love about this is we're going to plot the first point, but then we're going to convert it. We're going to do a little extra work. We're going to convert it back to xy coordinates, and then see if our point agrees with that interpretation. Holy shit. So we're first going to plot this point in polar. So the way you do polar is really strange, because we're not used to it. We're used to going over and up. Now we got to think about, first off, let's designate a scale for our radii. So you could, if you wanted to, you could make this a radius of 1, a radius of 2, a radius of 3. Something's going to be a little bit better here, and dear God, please, when we start to graph equations, don't have this little tiny thing, and you're like, you got all this blank. What? No, make a better scale. Use some room so you can get some resolution in there. What's my largest radius? 4. So I can use a big old chunk of this. So maybe we can use 1, 2, 3. This will be 1. So maybe you can go by 1/4, 2/4. Maybe we can go by 0.25. Is that all right? Let's see if that'll work. So this will be 1, 2, 3. 1. 1, 2, 3. 2. 1, 2, 3. You can do it, Jeff. 3. 1, 2, 3. 4. Okay. Let me make that a little bit bigger. 1, 2, 3, 4. So if I had a point, let me start with a point that's not even on there. If I had the point 0, 2, and it's in polar. Let me try this again. 2, 0. There it is. And it's r theta. So what would the angle be? 0 degrees. And where is 0 degrees? Here, right? That's why cosine of 0 is 1, because cosine likes x. So 0 means basically the positive x-axis. And how far do I want to go out? 2. So then it would be right there. That would be the point that describes. How are we doing so far? Okay. And actually it's the same point in rectangle. We're talking about the intersect. What about 3, pi over 3? So which way am I going to face? Pi over 3. So I'm going to face this way. And I'm going to go how far out? 3. So I want to, right there. You see, here's 3. So you could do it 2 different ways. And the way to do it that's easier, what I just did, when you go to graph it, is you can tell the dude, or the dudette, or whoever, whatever it is, and whatever can understand your commands. You tell, go out 3, and then turn through an angle of pi over 3. You can totally do that. You get to the same place. Or you can say, face pi over 3, and then walk out 3. So it's going to be right there. So I go out 3. I turn through an angle of pi over 3. You can do it, Jeff? Yay. Now, let's take a second. Let's label some of these around here so it makes it easier for later. 1, 2, 3, 4. Okay. What I desperately want you guys to understand, what's really nice about this is the minute you set up your radii, you're also setting up your XY plane. That's kind of behind the scenes here. What point is that approximately in XY speed? Looks to be about, well, it's a little less than 2, right? So maybe, and a little bit more, so maybe 1.6 or something. Do you guys see that? So this point right here would be right here, so maybe just 1.6, comma, what would be the Y piece? 2.6 or something? That's our rough guesstimate. You with me? All right, now let's convert 3 pi over 3. 3 comma pi over 3. Let's convert that to rectangular. And let's see if we get this. I really want you guys to see what I'm doing. So you can plot in polar. We just plotted that point using polar coordinates. But it should end up in the same damn place as if you used rectangular, the corresponding rectangular coordinates. So how do I convert that into rectangular?
R cosine.
Yeah, x would be
R cosine pi.
good. So 3 cosine pi over 3. And just go ahead and make this a decimal, right? Cosine pi 3 is 1/2. 3 divided by 2 is... Cosine of pi over 3 is 1/2. And 3 times 1/2 is 3/2, which is also known as 1.5. Pretty close. Right? Of course, our early picture. And what about 3 sine pi over 3 for the y? Little y. 3 times rad 3 over 2. Well, what's 3 times rad 3 over 2? Somebody help me out with a calculator.
2.6.
No way, it's crazy. So 1.5, 2.6 is basically what we got. I really want you guys to see. We're talking about the same damn point, so it doesn't matter what we call it. It means the same place in space. So some of you guys might be like, well, why the hell would you go and make weird-ass polar coordinates up? Because some problems are circular in nature, so they're actually easier to solve using polar coordinates. When you go to 3D, oh shit, you can have cylindrical coordinates, you can have spherical coordinates. It all depends on if your problem has some kind of geometry to it, where it's like little cylinders. I'm going to use cylindrical coordinates. It's insane. What do those look like, Jeff? I don't know. Google it. Well, I do know. I just don't want to talk about it right. We don't have to worry about 3D in here. And then spherical is even neater. Coordinate system. You can Google it too. I might bring in some other coordinate systems just so you can see what you don't have to worry about yet. Or if this is it for you guys, you never have to worry about it at all. Alright, so let's try this. Let's do one more of these together, and then I want you guys to finish these out. I'm sure there are some people that have already finished it out. How do you do the graph this point? Yeah, I go 4, and then I can go 3 pi over 2. So I can go right there and there. So I need some down here and see. I need some 1, 2, 3, 4. So if I want to go 4, 3 pi over 2, bam. Face 3 pi over 2 and go down 4. Now let me make sure you understand. I almost put a negative there. Even though you can see the xy plane, I'm not going to make this a -4 because that is a positive radius, right? What do you think it would mean, for example, on number E? I do know what he just said. On part E, what does that -3 mean? Walk backwards. Yeah. Alright, so you guys try out the rest. C, D, E, F. If you haven't already. Alright, let me catch up to you guys here. So to get part C, what do I do?
3.5.
Yeah, so I can go 3.5.
Bang over 5.
Yeah, so this one I'd rather go face pi and go 3.5. Bam. So there's part C. You label these bad boys. This is part A. B. What about, is everybody cool with that? Okay, can somebody tell me real quick, what's another way to say this angle? At this point, sorry. What's another way to identify that point? Not in XY, in polar. Is there another way to identify that point in polar coordinates? Negative 3.5, 0. So look straight ahead and walk backwards 3.5 steps, right? Which I want you to do. Does that make sense? So there's always at least one more way to write the point using a negative radius. And of course, how many coterminal angles are there? Infinite numbers, so that just gets silly. But to make a negative radius, I would call that a truly different way to write the point. So what about this guy? I can go out 1.5 and then turn 5 or 6. Bam. There's D. E. So do it. What's happening? Go down where?
Go to the left 3.
Alright, so go back 3.
And then go to 2 pi over 3.
Yeah, so this problem I would say it's easier to look at 2 pi over 3. And where's 2 pi over 3 on this side? You get 1, 2, it's 1, 2, it's there. Alright, so now I just got to go out 3. Bam. Either way you want to do it. Some points it's easier to do it one way, some points other ways. So that's point E. What about point F? Where's the negative 11 pi over 12? Where is it? Quadrant, which one?
3.
Quadrant 3, because it's not quite half a turn, right? It's not quite pi. So I'm going to go back. So it's 1/12 away from pi, so it's right here. This would be a negative 11 pi over 12. Is one way to reference that. And I want to go there and go out 2, so I go out 2. Bam. So the thing that freaks people out the most, I think, is having that curved scale. Once you identify what the radius is, 2 doesn't go like this. 2 it curves. Of course it does. And that takes a little getting used to when you do these. Now, obviously, hopefully you understand the next step on this. This computers take way too long. The next step would be to create equations and plot them in polar coordinates. So, for example, if I had the equation r equals 2 cosine theta, how do you think you would start plotting that in polar? What do you think a really good idea is, since we're not really sure what that looks like? Google how to do it in your calculator. No. Yeah, you make in this case it's going to be an r theta table. Make an r theta table. So at 0 degrees, what would the radius be?
0.
What's cosine of 0? 1. 1 times 2? 2. At pi over 6, what's cosine of pi over 6? Root 3 over 2 times 2? Root 3, which is approximately what? So now you can finally just give the decimals if you want to. It's fine. Because we're going to plot the damn things. In fact, you only want to give a decimal out to one place. If you can plot 2 decimal places on this graph, you're way better than I am. Right? So what is square root of 3 roughly?
1.7.
1.7? And so forth. And then you go plot each one of those like we just did, and you connect them, and you get some nifty ass shapes. You get shapes, like I said, from the old spirograph game. I know a lot of you guys never heard of it, but it's cool. It had gears within gears. That was the commercial for it. Gears within gears. Ooh, sounds like a workplace kind of thing. You enjoy working at Wendy's. So, sorry, I had a flashback.
Sorry.
they had a gear within another gear, and you put your pen in it, and you kind of, and the gears would move them and make certain shapes. And normally the shapes would look something like, something like, you know, grossly. That looks horrible, Jeff. But you understand. I think you understand. These little, like, flowery dudes, and you have some different stuff. We're actually going to create those pictures on our calculator. We're going to figure out what the equations are that will make that happen. I want to make a 3-leaf rose, a 5-leaf rose. I want to do all this neat stuff. I'm going to show you the equation that actually makes a butterfly shows up with your calculator. It's kind of cool. That I think is parametric. We'll get there. Really cool. All right. So I think it's enough. We'll have an early day today. You guys can go start corrections. The village of Detroit.